Alright, in this video we're going to look at how structure of the acids in terms of how their atoms are bonded together will affect their behavior in terms of their reactivity, their relative strength, and this correlates to bases as well in terms of basically being the mirror image of acids. So the first thing we're going to look at are binary acids, acids that just have hydrogen attached to an anion, and that would come from the periodic table. And basically the strength of the bond is going to play the biggest role in determining the strength of the acid. The more polar the anion is, the easier that bond is to break, and therefore ionize and produce hydrogen ions. The lone exception to this is HF, and that's because hydrogen fluoride can make hydrogen bonding occur within its molecules. So not only do you have the really electronegative fluorine not wanting to let go of the hydrogen atom, you also have those intermolecular forces to overcome as well. And so as a result, hydrogen fluoride or hydrofluoric acid is classified as a weak acid. It will dissociate to a slight extent, but not nearly as much as the other members of its group, hydrochloric, hydrobromic, and hydroiodic, which are 3 of your 6 strong acids. And this would play a role like with H2S and H2SE. H2S would be a stronger acid than H2SE because the bond is not going to be as polar with H2SE as it was with H2S. With oxyacids, it has to do with how many oxygen atoms are present in the structure. The more oxygen atoms that are present, the more electronegative atoms we have, and the more the electrons get pulled away from that HO bond and more towards the nonmetal and the oxygens that are attached to it. So when the electrons are pulled more away, you are able to break that bond more easily. And so you see here in these examples with the chlorine oxyacids, HClO4, which is another one of our strong acids, isn't assigned a K value because it pretty much completely dissociates. Chloric acid also is a fairly strong acid, but it is classified as a stronger, weaker acid. Chlorous acid has one less oxygen, so the bond becomes not as polarized. And then with HOCl, we see that we only have that one oxygen attached to chlorine, and so its K value rapidly drops, becoming much weaker as an acid. The other factor that plays a role with oxyacids is the nonmetal that is attached to the oxygen. The more electronegative that nonmetal is, the more it's able to pull electrons away from that HO bond, because the side of negative charge will be over with that nonmetal, and therefore it's easier to break that HO bond. So in these 3 particular oxyacids, HIO, HBRO, and HClO, Cl is the most electronegative of those 3 nonmetals, and therefore it is able to have a more polar bond between the HO, and therefore a larger K value. It still is a weak acid, but comparing that to HOBr's K value and HOI, we see that HOCl is the strongest of these 3. I will never ask you to do something like HIO2 and HClO3. I would either ask you to compare oxyacids with different nonmetals and the same number of oxygens, or I would ask you to classify oxyacids with the same nonmetal and different numbers of oxygen atoms. So let's look at a couple of examples here. We have HBrO2 and HClO2, and I want to know which one would be the stronger acid. The oxygens are the same, so we're looking at our nonmetals, and chlorine is more electronegative than bromine, so we would expect it to be the stronger acid because it's going to be able to pull the electrons more away from the HO bond. And so because it's more polar, it is more acidic, HBrO2 would be a weaker acid compared to HClO2. So this time we're going to look at oxygen atoms. We have H3PO4 and H3PO3. H3PO3 has one less oxygen that can pull electrons away from the HO bond, and so therefore it is going to be able to polarize that bond less. As a result, that HO bond is going to be more stable in the H3PO3 molecule than it will be in H3PO4, and so the stronger acid would be the H3PO4. Now, if we look at it from the opposite approach, SO42- and SO32-, we see that SO42- has one more oxygen atom, so trying to get it to accept a hydrogen proton is going to be more difficult than SO32- because of that site of negative charge that's going to occur. It's going to be more negative on the SO4 molecule with the extra oxygen atom, and therefore make that bond more easily polarized than it would have with SO32-. And so because that potential HO bond is less stable with SO4 2- than it is with SO3 SO4 2- is the weaker base, and SO3 2- is the slightly stronger one. All right, and so that's the end of this particular section, and that should get you to the last worksheet in part 1 of your assignment packet.